What we start with is the level surfaces domain. So we do, and what I'm expecting to happen on this exam, level sets. That means it could be curves or it could be surfaces. Surfaces when you have functions of more than 2 variables. Levels curves when the function is of 2 variables. So that's why we call them sets, because it can be surfaces or curves. And then now, what else do we know for this section? So we do level curves, we do contour map, we do domain and cross sections. That's for this 14.1. For 14.2, we do limits. Limits of basically, when we start with limits for elementary functions. Basically, the functions that are the known functions to you, right? The ones that are not piecewise defined. Those are the elementary functions. And they are in their domain continuous. So we start with that. It's sort of the opposite way of Calc 1, but the theorems that underlying theorems tells you it's all okay to do that. Then we discuss forms 0 over 0. What I want to say in this section is this. I'm going to move down here to show limit does not exist of form 0 over 0. Give 2 paths that have a different different limits. To show limit exists, I'm going to give you a little bit of trick in this course, because there are all sort of different questions can be posed when limit exists. There are limited knowledge that we have through this course, and there are unlimited knowledge if you guys are willing to do a lot of algebra. So I'm just going to go for preparation for the exam, and also it prepares you for specific type of questions in your future after Math 127 is over. I try to stick to one method to show the limit exists for the exam. And that is, I'm going to ask you to use polar coordinates for 0 over 0, right? Polar coordinates. Simplify. And then possibly use squeeze theorem. A lot of things can be solved through this method, and that's why it has just sticking to the limits that uses this serves us something for future. And then telling you my trick right now, it makes it easier on you to recognize that on the exam. Okay, so again, you showing me that 2 paths have the same limit doesn't do anything. It's just 0 value. 2 paths have different limits, then you prove the DNE, you show DNE. To prove that limit exists, you have to do some more. That's the difference. So there are stories that we discussed also. We discussed partial derivatives as the slope. of the tangent line in x direction or y direction. That's why this tangent line basically has direction vector f sub x of a and b. That tangent line has direction vector 0, 1, f sub y of a and b. We discussed the notation for partials. I think I put it over there. Notation for partials, either you can use f sub x, f sub y, or you can use partial of f with respect to x, partial of f with respect to y. Then if you want to go to higher derivative, take the derivative with respect to x first, then another x. Or you can go x first, then another x. fxy would be with respect to x, then with respect to y, and so on and so forth. Then we had this convenient theorem that said if the second derivatives are continuous, then it doesn't matter. So Euler's theorem. Oh, let me write it here. So Claire's theorem. If eigenpartials are continuous, then as long as you're taking the mixed partials, as long as the variable you're taking derivative with respect to appears the same number of times, the order doesn't matter. So that was the beauty of it. Now, that said, what else is in this sections? Tangent plane. Tangent plane, and one formula is given in the in section 14 point. Sorry, starts getting itchy. When you can't touch your face, it's always itchy, right? Is that, yeah? And so there are multiple formula. There are multiple methods. We showed two methods of finding tangent plane. And then in the worksheet, you realize, oh, they're both the same thing, basically. So you can remember one of them, and one of them is better, is just, in my mind, is easier to go. That's when I put all the variables in one side, take the gradient, use the gradient vector to find the tangent plane. So I'm going to use that method. Then comes all these stories of basically differentials and linear approximations. So linear approximation is just the equation of the tangent line solved for z. Then you can use that to find the differentials. So let's say if I find the equation of tangent line, I said tangent line, I'm sorry, Cat3. If I say tangent line, I have to tell you direction for Cat3. So it's tangent plane. So now, if I find the equation of the tangent plane, it's just z equal to f sub x of a and b times x minus a plus f sub y of a and b times y minus b plus c. C would be the z value for the at a and b. Now here, if I take this and show that by delta x and show that by delta y, right? Then I get z equal to, sorry, and subtract c from the other side. Z minus C is going to be f sub x of A and B times delta x plus f sub y of A and B times delta y. But Z minus C is dz. If you have functions of more variables, you just repeat this process. Tangent plane becomes hypertangent plane. And linear approximation stays on still linear approximation. So that's the routine that you do. So that's why those formulas come in. So you don't have to memorize those formulas. They just generalization of these formulas, basically. You don't have to memorize them. That's important to know. That said, what am I not haven't I covered? It's the directional derivative. So what is a directional derivative? Directional derivative, oh, gradient vector. What is a gradient vector? If f of x and y is differentiable, then gradient of f is going to be f sub x at x and y, and f sub y at x and y. Gradient of f at a and b is going to be f sub x of a and b, and f sub y of a and b. Now, if you have functions of more variables, then the gradient is going to be f sub x, f sub y, f sub z. X, y, z. Now, beauty of gradients is that gradient vector at a point is perpendicular or orthogonal to the surface, level set of that thing. This one has a level curve, that one has a level surface. That's why I'm saying that. So that one level curve, that one level surface. As soon as you go one variable up, it gets bigger. So gradient at a point, gradient of function at a point is perpendicular to the level set of the function. And you cannot see anything I'm writing. Thank you for mentioning it. That point. So yeah, gradient comes in handy. It comes back to you a bunch of times. In chapter 15, we keep it away for a while. It comes back heavily in chapter 16 and 17. So it's worth your time, basically. William, are you talking? Did you ask a question, Mark? Okay, so they are answering their own questions. I didn't even see that. Okay, I'm gonna move on to the next. I know that I can hear you, so you can unmute yourself and ask. And the crowd too, please. And so the last thing in here is the directional derivative in direction, let's say u. If I'm finding directional derivative of a function in direction u unit vector, if it's not, make sure it is becoming the unit vector, then you want to evaluate it at a point A and B or A and B and C. However that is, basically. This is going to be the gradient of f dot u at A and B and C. I didn't put it in front of gradient of f. So that's the basic reminder of the. Oh no, I didn't do one more thing. let's talk about this directional derivative means that if I take one step in direction u, how much z is going to change, and it's instantaneous change, right? So it's instantaneous rate of change in that direction. If I go hypothetical one step, then that's how my z is changing. It turns out, and we proved it before, because the dot product, the other formula for the dot product, we proved that gradient of f basically is the direction. It's not the unit vector direction, but it's the direction of the fastest increase. And then that fastest increase, when we computed, was just magnitude of gradient of f. The negative gradient of f is the direction of the fastest decrease. So however you're going to get uphill, it's the worst uphill, whatever direction you're using for the worst uphill direction. Opposite of that is the best downhill position. And that comes in handy in a ton of ways. And so that rate is negative gradient of f. I think I covered all the material. Let's move on with limits. Are you guys ready for limits? So let's do limits. I'll put this here. I keep telling you this little recognition methods. Why is this? Because in this course, I'm always, do you remember from Calc 1 when there was polynomial on top, you had a quotient, polynomial on top, polynomial on bottom. We give you 3 different ways to find the limit. That was even in pre-calculus, as limit goes to infinity or as limit goes to a number, we would give you methods, right? Now, here when you have form 0 over 0, there's a few things that doesn't require extreme algebra that we can give you to do. And one of them is that if the limit doesn't exist, and one of them is when some of them require limit doesn't exist, some of them require limit exists. My rule of thumb here is this. Do you see that I have x to the power 2, y to the power 2